Okay, so today we are doing a problem on heat conduction. Heat conduction. So we are considering a solid sphere of radius r. And so we have a solid sphere of a material with thermal conductivity. K, and we assume that K is a constant. So this sphere is cooled by flow, and this flow is of a certain temperature T infinity, and we assume that T infinity is a constant, and this flow cools the sphere with a certain heat transfer coefficient H, and so H is also constant. So further hypothesis is that we have a steady problem, so we can neglect the partial derivative with respect of time, and we also assume that inside the sphere there is a certain mechanism of generation of heat, and this depends on r. So r is the coordinate, is the radial coordinate r. We also assume that the generation of heat is not constant but depends on the radius as follows. R minus R multiplies a certain constant A. So A is a constant. So when R equal big R, then heat generation is 0. But when R is 0, the heat generation is maximum. So when R is equal 0, then we have the maximum generation of heat, and that's equal to A times R. Okay, so the objective is to find T as a function of the radius R, where T is the temperature. So we're considering a one-dimensional problem. One-dimensional because the temperature only depends on the radial direction r. So what we have to do, we have to solve a differential equation, and that's the heat conduction equation. Heat conduction equation. And in spherical coordinates for a steady problem where the thermoconductivity K is a constant, then we have 1 over r squared dt dr K r squared dt dr, and this is added, the heat generation equal 0. But since K is a constant, then it can be taken out of the derivative, and we can divide both terms by K. So we find 1 over r squared ddr r squared dt dr plus E dot heat generation divided by the thermal conductivity H, K. So since we know the heat generation, how it depends on the radius r, we can substitute the function that we know. So we have plus a r minus r divided by k equal 0. So now that we have our conduction equation written, we need to specify boundary conditions. And since this equation is of second order ODE, we need two boundary conditions. So boundary conditions. So the first boundary condition is at r equal 0. So this is the center of the sphere, and the boundary condition is minus k dt dr equals 0. So this means that at r equals 0, the center of the sphere, dt dr is 0. So there is no gradient of temperature right in the middle of the sphere. So we note this is because there's no heat transfer. There's no heat transfer in the middle of the sphere. So thanks to Fourier's law of conduction, we see that also the gradient is 0. And we also note that r equals 0 is a point of symmetry. So another point of symmetry, for example, if we solve the problem in Cartesian coordinates in the wall, can be right the plane, the center line plane, or for a cylinder is the axis of the cylinder if you have 1D problems. So the other boundary condition is at r equal big R, so at the outer surface of the sphere. And here we have a conduction, convection boundary condition. This means that the heat is conducted through the solid of the sphere and then is transported outside thanks to convection. So if you do energy balance on the surface of the sphere, then we obtain the following: minus k dt dr at r equal big R must be equal to h T temperature evaluated at big R minus T infinity, where T infinity is the temperature of the flow of the fluid that's cooling the air far away from the surface of the sphere. Okay, so at this point we can proceed to integrate the equation. So the next step is to multiply both sides by r squared. And so we can take on the other side. So we have d dr r squared dt dr equal r cubed minus r squared divided by k times a. Okay, so at this point we can integrate once. So we have r squared dt dr equal a r to the fourth power divided by 4k minus a r cubed 3k plus a constant of integration c1. Since this is multiplied by r squared, we can divide by r squared. We have dt dr equal a r squared divided by 4k minus ARR divided by 3k plus C1 divided by R squared. We can integrate again and we find T of R equal AR cubed divided by 12k minus ARR squared divided by 6k minus C1R plus C2, where C2 is the second constant of integration. Very good. So now we have this expression. We have to find C1 and C2, and to find C1 and C2 we use the two boundary conditions. Let's see how we do that. So we use the first boundary condition, so we have to set dt dr at r equals 0 equal to 0. So we differentiate the expression we found for the temperature. We find AR squared divided by 4k minus ARR divided by 3k plus C1 R squared equals 0. So these two terms go away because R is 0, and then we find C1 divided by R squared equals 0. So we find that C1 is equal to 0. So because otherwise there would be a singularity, and so this is impossible, it's equal to 0. So the second boundary condition, minus k AR squared divided by 4k minus ARR divided by 3k at R equal big R must be equal to the convection. That's H AR cubed divided by 12k minus AR R squared divided by 6k plus C2 minus T infinity. So here already we don't include the term that has C1 because we found already that C1 is equal to 0, and this is evaluated at R equal big R. So what we have to do now, we substitute R inside here. That's a bit of algebra, and we need to solve for C2. And we find that C2 is equal to AR squared 12k plus AR cubed divided by 12k. Sorry, this is H. Okay, plus T infinity. And so we have C2. So we found C1, we found C2. So we have the temperature distribution, that's T over R equal AR cubed divided by 12k minus AR R squared divided by 6k plus AR squared 12k 12H plus AR cubed 12k plus T infinity. So this is good results. We found it. Okay, so we can sketch this, and the temperature distribution inside the sphere looks like this. We have a radius R, so we can plot. So at R equals 0, we already know that here it's clear. The gradient of the temperature with respect to R is 0, and That's also the point which temperature is maximum. So this can be shown, and so the temperature distribution looks something like this. Okay, so here we have a negative gradient. This means that heat flows outside of the sphere. So heat generation inside is taken outside by convection. So we can find the temperature at position big R, and that's AR squared divided by 12H plus T infinity, and also at 0, that's AR squared divided by 12H plus AR cubed divided by 12K plus T infinity. So the difference between these two temperatures is this quantity, and that's exactly this jump in temperature. Okay, so this is AR cubed divided by 12K. So this is the jump in temperature between the maximum at the center of the sphere and the minimum temperature that occurs on the surface of the sphere. Excellent. So a good exercise would be now to check, so that's usual practice, check boundary conditions if they're satisfied. And so this is actually can be verified, so let's do it. So at R equals 0, dt dr at R equals 0 must be 0. So we have AR squared divided by 4K minus ARR divided by 3K, and this is equal 0 because R is 0. And the other R equal R is also satisfied, so you can try this. So left for exercise. Very good. We can check that dt dr is smaller than 0 at R equals 0. R equal big R. And indeed we have dt dr equal AR squared divided by 4K minus AR squared divided by 3K, and so this is smaller than 0 because A is a positive constant. A further check is a control volume check. This means that, so we have a sphere, and if we take as a control volume the sphere itself, the heat that leaves the surface in watts must be equal to E dot. So this is the heat generated inside, also in watts. So we can check if all the heat that generated inside the sphere is equal to the heat that leaves the surface. So how do we do that? Well, the heat generated is equal to the integral over the volume of the heat generation. So this is equal to the integral between 0 and R of R minus RA, and this is the heat generation per unit volume times the differential volume, that's 4 pi R squared dr. Okay, and the Q that leaves the surface at R equal R, it's equal to minus A K 4 pi R squared dt dr. Okay, so if you do this integral, you find that this is equal to minus pi ar to the 4th power divided by 3, and this is also true. This is the same, and you also, this is left as an exercise. Okay, that's it for today. Thank you very much.